Hi everyone, my name's Peter Fall and I'm one of the authors of the sFlow measurement standard we'll be talking about. I'll start with an overview of sFlow technology and end with a demonstration showing the technology in action as we troubleshoot performance problems in a GPU cluster. Before diving in, it's worth understanding the problem that sFlow is trying to solve. My background is control engineering, and this diagram shows how a control engineer views the task of managing a high-performance compute cluster. In this case, the system is the set of compute nodes and the network that connects them. Measurements are needed to understand how the system is performing. The measurements are analyzed, and if a problem is observed, a plan is developed, and then a configuration action implemented. New measurements are used to confirm that the problem's been corrected. This feedback loop operates continually to maintain optimal performance. Whenever you build a feedback loop, you need to meet certain requirements in order to ensure stability. First, and this is where sFlow comes in, you need to be able to monitor all the important system states. Incomplete measurement data means that you might miss critical information. At this point, an analogy might be helpful. When you drive a car, you're providing feedback that controls the car. Observability requires that you can see the road ahead, the mirrors, and the speedometer so that you can safely drive. The second requirement is that the system needs to be controllable. There need to be mechanisms that allow you to alter the behavior of the system based on your observations. Going back to the driving analogy, a steering wheel, accelerator, and brakes are needed. If any of these essential controls are missing, you can't drive safely. The final requirement is that the feedback loop is responsive. This means that the time between a problem occurring and the control action taking effect needs to be fast enough to manage the state of the system. Using the driving analogy again, you need to react quickly if the car ahead brakes in order to avoid an accident. We can now understand that sFlow is a monitoring technology designed to make networked systems observable, providing the comprehensive low-latency measurements needed to drive automation. This diagram shows the elements of the NVIDIA GPU compute cluster we'll be demonstrating. Cumulus Linux running on the switches reduces operational complexity by allowing you to run the same Linux operating system on the network devices as is run on the compute servers. sFlow telemetry is generated by the open-source host sFlow agent that runs on the servers and switches, using standard Linux APIs to enable instrumentation and gather measurements. In the sFlow architecture, the agents are simple and stateless so that they can be embedded throughout the infrastructure and provide the continuous low-latency telemetry needed for observability without imposing a significant overhead that would impact performance. In this case, telemetry from the entire system is streamed to the sFlow RT analyzer, which builds a real-time view of performance that can be used to drive operational dashboards and automation. Next, we'll look at the types of measurements making up the sFlow telemetry stream. Counters are a staple of network system and application management. In the network, the hardware maintains counters for each interface. On a host, the operating system maintains counters that track CPU, memory, and disk activity. The NVIDIA management library provides access to counters maintained by the GPU hardware. Applications maintain counters of the number and types of requests being handled. The counters are not actionable if they're stranded on each network, switch, server, or application instance. What's needed is an efficient method of exporting the counters. This is where sFlow comes in. sFlow is a simple measurement protocol that allows the sets of counters shown on the previous slide to be efficiently exported. Each of the blocks of counters is exported in a densely packed structure and sent to the sFlow collector in a real-time UDP stream. Minimal configuration is required. The agents need to know where to send the counters and how often to send them. Observability is ensured since each agent starts sending data as soon as the device starts, making sure that the device is immediately detected and continuously monitored. This slide shows traffic on a 100 gigabit per second network link. Counters are popular because they summarize enormous amounts of information. In this case, nearly 1 billion packets are summarized in each 1-minute segment of the chart. The chart's useful in that it lets us see that the traffic is spiking. but it's not actionable because we don't know what type of traffic this is or where it's coming from. To get to the root cause of the traffic spike, we need a way to disaggregate the counter that can scale to millions of events per second. sFlow solves this problem by adding randomly sampled packets to the telemetry stream. The graph shows an analysis of sampled packets from the link, breaking out traffic by addresses and ports, making it easy to see that the increased traffic is due to 3 roughly equal UDP packet streams, each sending around 40 gigabits per second. This is the information needed to take action, since we can now go to the traffic sources and rate limit, reschedule, or reprioritize the traffic as appropriate. Random sampling is a very simple, stateless method of measurement that's easily implemented in hardware. The statistics of sampling are well understood, and sampling easily scales to large numbers of devices and very high packet rates. Support for random sampling is built into the Linux kernel for host monitoring. On switches, the sampling function is accelerated by hardware for line rate performance. Today, I'm really excited to be talking about a third type of measurement that we've been working with Mellanox to add to sFlow that fills in a critical observability gap. Random sampling is very good for managing load. A heavily loaded link will generate many samples that can be used to rapidly identify the source of the traffic. However, managing packet loss has been a challenge. Dropped packets are rare and unlikely to be sampled. However, a single dropped packet can severely impact the performance of the application whose packet's been dropped, reducing or even preventing packet flows and making it even less likely that the affected traffic will be observed. The packet drop counters in the sFlow telemetry stream tell you that packets are being lost in the network, but don't tell you why. Recent instrumentation added to the Linux kernel and offloaded to hardware on Mellanox switches solves this problem by including instrumentation that captures dropped packets, along with the reason the packet was dropped. The new sFlow packet drop event adds this information to the sFlow telemetry stream, making it possible to identify a single dropped packet, even on a busy link carrying millions of packets per second. The graph on this slide shows a single dropped TCP packet due to an attempt to connect to a non-existent web server. This could indicate that the service has failed, that the client's misconfigured, or it might indicate reconnaissance by a hacker. Being able to monitor dropped packets on hosts and then in the network gives a complete end-to-end view of packet discards wherever they might occur. 3 types of telemetry, counters, random samples, and drop notifications, are part of a unified system. The sFlow specification includes an integrated data model that combines the measurement streams so that they can be correlated and provide the observability needed to support automation. Most data center networks include equipment from more than one vendor. sFlow is a mature and widely supported standard that's integrated in network hardware. Broad multi-vendor support for sFlow ensures that all devices that are part of the automation scheme can provide the observability needed for stable control. The open source host sFlow agent extends visibility onto compute platforms, leveraging instrumentation in the Linux kernel, GPUs, network adapters, and applications so that compute and network can be managed as an integrated system. And now for the demo. We'll be looking at real-time data from the GPU cluster. The host sFlow agent comes pre-installed on Cumulus Linux and has been installed on the servers. The configuration file installed on the switches and servers directs each agent to stream sFlow telemetry to the collector. The sFlow RT real-time analytics software is available as a pre-built Docker image. Installing and running the software on the collector host is a simple one-line command. The web interface is now accessible on port 8008. The 3 charts in this dashboard update every second to show GPU utilization, calculated from sFlow counters, network activity, calculated from sFlow packet samples, and packet discards, calculated from sFlow packet drop notifications. The charts pull together data from all the network and compute nodes in the cluster to provide a cluster-level view of performance. The activity shown is due to a video processing workload. Video is streamed across the network to a compute node, where GPU-accelerated software transcodes the content and returns the result. Each time a new job starts, you can immediately see a jump in network traffic and GPU utilization. The current transcoding jobs run into difficulty. The GPU load is down, and no data is being transferred. Looking at the network drop chart, we can see that the access control list has dropped the packet, initiating the connection and blocked the transfer. We can also see the agent field identifying the switch that dropped the packets. Looking at the switch console, we can see the access control that was previously installed. We can now type a command to delete the control and apply the new configuration. Removing the access control on the switch should restore service. We can confirm this by looking at the dashboard. The charts confirm that the fix has taken effect because we no longer see packet drops. Data transfer rates have been restored, and the GPU activity is now back to normal. This demonstration shows how the performance of a GPU cluster depends on the network. Real-time cluster-wide visibility from sFlow agents embedded within the switches and servers delivers the observability needed to quickly identify and correct issues in order to maintain optimal performance.